Hello, my name is Philip Shilane, and this is joint work with Hyong, Shim, and Windsor, completed at EMC Corporation. So let me begin by discussing data protection environments. So for most customer situations, they have application servers connected by a storage area network or a local area network to a primary storage system. And the primary storage system may have tens or hundreds of terabytes or even petabytes of capacity. And that capacity is then subdivided into storage volumes. Each volume may be allocated to perhaps a database, email server, or file server in this example. Now, what are some of the properties, high-level properties of primary storage? We often consider we have to have high I/O per second requirements. And while capacity is important, it's often lower priority than high I/O. And this is because customers are using their primary storage to drive their business. Either this is what their customers see or what engineers are using to develop the next product. And so they're willing to spend a fair amount of money to get a good quality primary storage system. And to protect against site disasters, such as a fire, it's important to make copies off-site to a remote location to data protection storage. And so the properties of data protection storage are a little bit different than primary storage. Capacity has to be very large because it has to hold multiple copies of the primary storage system. And while we'd like the I/O per second to be as high as possible, it's prioritized lower. And this is because customers just won't spend as much money on backup storage as they do as primary storage. Otherwise, everybody in this room would be doing research into backup storage like me. So we have to make these trade-offs: large capacity, lower I/O. So in order to protect their data, they begin by making a full backup of all of their storage volumes over to protection storage. And then perhaps based on some policy of daily or hourly incremental backups, they then copy over the small changes that have taken place since the last backup. So the point of this research is to investigate what is the nature of these incremental backups, how much data needs to be transferred, what are the overheads on primary storage related to making these incremental transfers, what's the network bandwidth required across the WAN, and what are the properties for protection storage that actually matter. And while I'm talking mostly about primary storage, you could substitute in the term virtual machines, because you have to also protect virtual machines in a similar way, and with change block tracking, you could transfer the changed blocks. So we have a few high-level contributions I want to mention. So we analyzed a very large number of traces from customer sites. And we designed a new version of snapshotting to reduce overheads on primary storage that we call replication snapshots. We also used our traces to analyze overheads on protection storage, and we can gain better insights into how to design protection storage in the future. In the paper and in this talk, there are a lot of experiments, there are a lot of analyzing this property and that property, and it can become somewhat confusing, so we try to come up with some very high-level coarse rules of thumb. And these rules of thumb focus on the kind of average case or typical case, and we do some rounding, so hopefully the rules of thumb are memorable. So let's begin by looking at some of the traces we had for analysis. So these traces were gathered from EMC customers that had purchased Symmetrix VMAX primary storage machines. So these are tier 1 primary storage machines. So the first row of this table, we had a large number of traces. We subdivided them into traces that lasted at least 1 hour and had at least one write. And there were over 100,000 storage volumes, and those storage volumes existed on 125 systems. So by storage system, I mean a single VMAX machine at a customer site. And the average duration was 30 hours with a standard deviation of 78 hours. And the estimated capacity was 71 gigabytes for these traces. Since we were focused on looking at incremental changes, we further subdivided these traces into the set that had at least 1 gigabyte of writes. And now we're down to 16,000 storage volumes that had traces. And then we're interested in looking at how data changes over time, so we required that a trace lasted at least 24 hours. And so now we're down to a little bit more than 500 storage volumes that had traces from 13 VMAX systems. And I should point out that these traces were gathered from customer sites, and so unfortunately we can't make them public as of now, but we are happy to work with students, and you can talk with me about that afterwards. So let's just look at a few high-level properties of these traces. So first we analyzed the capacity of these storage volumes. So the horizontal axis is the size in gigabytes, the vertical axis is the percent of volumes, and you can see that most storage volumes are in the tens or low hundreds of gigabytes in size. So although the VMAX system maybe had hundreds of terabytes or petabytes of storage, customers typically subdivide it for management purposes. We next analyzed the write footprint. So we looked at what unique sectors were actually written during the tracing period, and you can see that it's in the low gigabytes or perhaps tens of gigabytes in size. So this suggests that although a storage volume may be hundreds of gigabytes in size, writes tend to be highly localized during any 24-hour trace period. So I'm not going to go through all the numbers in this table, but I just want to point out some properties that you could look in the paper to see in more detail. So we analyzed the number of write requests, average of 72,000 write requests per trace, the write size in gigabytes, read requests, read size. And then as we move down through the rows of the table, you can see that the numbers increase because we've become more restrictive. We require that there were more writes and the traces were on average longer. So a few high-level details to pull out of these tables. One, we found that there are 2 to 4x more read IOs than write IOs, which is consistent with previous literature in this area. And similarly, there's between 2 and 4.5 times more gigabytes read than written. And if you look at the numbers in brackets, that's the standard deviation, you can see that's often an order of magnitude larger than the average. So there's very high variability from trace to trace. So although I'm going to show results for the average traces, we decided to also focus on subset traces that had various properties to look at what happens with these high standard deviations. And there's much more analysis in the paper. So one of the properties we decided to look at is the impact of sequential versus random write IO. So really, what is the definition of sequential IO? We found multiple definitions in the literature, and so we came up with what we consider to be a fairly simple definition, that we look at how much data are written on average after making a random seek. And then we selected the most sequential traces and the most random traces and analyzed those separately. So let me just go through a quick example of how we calculate the sequentialness of a trace. So we have a storage volume that has sectors going from left to right. And we're going to have our counter on the far right here. So write comes into a single sector, then a write to the next consecutive sector, so we're still sequential. And then we have a larger write to 3 consecutive sectors. And then we had a random seek and then a read, so that's the end of a sequential write of length 5. And then we had another random seek, and we have a write, and another random seek, and so we've finished the write of length 1. Now we're considering the write of length 3, and we're at the end of our trace period, and so that's also a sequential write of length 3. And so on average, we have our metric would say this has a score of 3. So we selected the most sequential and the most random traces for separate analysis. So let me go through our trace analysis methodology, because this really drives all of the experiments in our paper. So we have a storage volume shown on the bottom, and we're going to show a trace timeline moving from left to right. So write enters the system and touches several sectors. Now, in a storage system, it's largely impractical to keep track of dirty sectors because there's just so many sectors in a large storage system. It would overwhelm memory. And so sectors are often grouped into larger units called blocks. And if a single sector in a block has been modified, the whole block would be marked as dirty. So we've marked it now in blue. And this is done for basically memory efficiency. You only need 1 bit per block as compared to 1 bit per sector in a simple bit vector implementation. So both blocks are marked as dirty because at least 1 sector in each block was modified. And I should say that in our experiments, we actually experimented with a range of block sizes from as small as a single sector up to 1 megabyte in size. So another write enters the system, goes to another set of sectors towards the end. Those are marked as dirty. Then we have a read, and in our analysis, we're entirely ignoring reads because we're only looking at incremental changes. Another write, and this write is an overwrite to a previously modified block. And so we could colloquially say that the block has become more fully dirty. And another write comes in, and this time the block has become completely dirty. If we had fine-grained tracking, we'd be able to keep track of that information. And now we're at the end of what we call a replication interval. The customers decided that they want to perform a backup once a day, and that's our replication interval. So at this moment in time, we want to have a point-in-time copy of the modified data, and that's what will get transferred to protection storage. So all of the blue blocks need to get transferred. And the important property is that that transfer can take a while. Right? It could take seconds, minutes, or even hours, depending on the change rate and the network bandwidth. And during that transfer period, we can't just freeze our storage system. We have to allow continued writes. So the way to protect these values, these dirty blocks, is typically to create a snapshot. And replication intervals tend to be back-to-back. So again, we have to track the changes that happen during the second replication interval with a secondary structure. So maybe we have two different bit vectors that we're switching between as we go between replication intervals. So a read enters the system, and then we have a write, and this write to our storage volume causes snapshot storage and snapshot I/O, because that's how snapshots are typically designed to protect against any writes against the snapshot. And then we have another write entering the system, and that's to a dirty block, and again causes snapshot storage and I/O. And you'll notice that these are really two different cases. The first write was to a clean block, the second was to a dirty block, and yet standard snapshotting would treat them equivalently. And then the trace continues. There are more writes and reads. At the end of the transfer period, we transferred all the previous dirty blocks, and now we have to mark the current dirty blocks, and the process continues. And I should say that for the transfer period, that really depends on the network bandwidth. And in our experiments, we consider network bandwidths as low as T1, 1.5 megabits per second, and up to a gigabit per second. And remember that this, even a gigabit per second, may seem potentially low, but that's per storage volume. And these primary storage systems have hundreds or thousands of storage volumes. And our replication intervals we considered were as short as 15 minutes and as long as 24 hours, and I'll show that in our experiments. So let's discuss improvements to the standard snapshotting technique that we call replication snapshots. So our goal is to create an improved version of snapshotting that is integrated with replication so that we can decrease these overheads on primary storage. And I want to point out a distinction between change block tracking and snapshotting. With change block tracking, you only have to keep track of which blocks are modified. And again, that might be as simple as a bit vector, which blocks are modified. But for snapshotting, we have to protect the data values. And so that requires some sort of storage to keep track of versioning of the data blocks. All right, so let's go through an example of the standard baseline snapshotting technique. And the issue is that all writes will cause a copy on write or a redirect on write. I'm going to talk mostly about copy on write, but the paper also discusses the differences with redirect on write snapshotting. All right, so we have our snapshot area, and our transfer is in progress. We're trying to transfer all the blue dirty blocks to protection storage. And during that transfer period, a write comes into block 1 that needs to be copied to our snapshot area. And a write to block 2 is also copied. And our transfer continues. And then a write to block 3 is also copied. So now we've copied 3 blocks into our snapshot area. So let's consider a simple improvement to standard snapshotting, what we call change block replication snapshot, where we're only going to track the modified blocks, the blue blocks, and only those need to be protected against overwrites. So again, our transfer is in progress. Write to block 1 is to a clean block, so nothing needs to be copied. Write to block 2, the same holds. Then write to block 3, this is to a dirty block, so it needs to be copied to the snapshot area. So we've improved the amount of storage requirements from 3 blocks to 1 block in this toy example. And so then we considered a further improvement that we call change block with early release. This involves much finer grained tracking of which blocks have already been transferred. Once the block is transferred to protection storage, we can unmark the tracking property, and then writes to it don't have to cause any snapshot I/O or storage. So again, our transfer is in progress, and a write comes into block 1. And now as soon as we've transferred block 0, we can unmark it as dirty. Write to block 2, the same. And now we've transferred block 3. And then the write to block 3 is to a clean block, so nothing needs to be copied to snapshot storage. So in this example, we've reduced the amount of snapshot storage from 3 to 1 to 0 in this example. All right, so let's get into some results looking at all of our traces. So the horizontal axis shows the replication interval increasing from 15 minutes up to 12 hours. The vertical axis is the fraction of the volume capacity that has to be set aside for a snapshot. And at the top, I have our rule of thumb. So again, this is a fairly abbreviated rule of thumb that you have to over-provision primary capacity by 8% to handle snapshots. So in this, the first line I'm showing is with a very small block size of a single sector, 512 bytes. And you can see that the storage capacity required grows to about 4% of 12 hours of replication. If we consider a much larger block size, 1 megabyte, you can see that it's as high as 8% overheads for capacity. And we considered all block sizes and powers of 2 between 1 sector and 1 megabytes. And those lines fall naturally between these 2 extreme points. If we consider our improvement, change block snapshotting, you can see the green lines are lower at 4% and about 2%. And then if we consider our further improvement, change block with early release, this further lowers storage overheads. And in all examples, having a larger block size has requires more storage overhead than a smaller block size. And that's because blocks are perhaps only partially dirty. Even if there's a single write to a block, the whole block needs to be copied to the snapshot area because that's our unit of tracking. So smaller blocks allow finer grain tracking. So the previous results were for all 500 traces. Now I'm focusing on the highly sequential traces. And you can see that the lines are more tightly grouped. The red lines are at the top, green lines in the middle, blue lines towards the bottom. And you can see that the block size is largely irrelevant because the highly sequential traces are just filling up sector after sector sequentially. The block size doesn't matter. The blocks are largely completely dirty. But again, improving the snapshotting technique lowers storage overheads. In contrast, if we look at the highly random traces, you can see the block size has a huge impact. Using the baseline snapshot, the red line grows to as much as 10% storage overhead, whereas with a small block size of 512 bytes, it's down to about 1% storage overhead. Because in this example, random traces, random I/O, might just touch a single sector out of a 1 megabyte block and just jumping from block to block. Next, we'll consider the I/O overheads on primary storage. And people often neglect the I/O overheads, but we found that it's necessary to over-provision by as much as 100% on the primary storage system if you want to support a given level of I/O the customer is demanding. And this is because, due to copy on write, you have to first read back, when a write comes in, you have to read back data from the primary storage system and copy it to the snapshot area, and then apply the incoming write. So there's a write amplification involved with copy on write. And redirect on write has some related overheads as well, discussed in the paper. So in this figure, the vertical axis is the fraction of incoming writes that cause a copy on write. So this is the write amplification. And the line at the top is close to 100% and drops off to about 90% with 12 hours of replication. And in this example, actually having a smaller block size has higher I/O overheads than a larger block size, which is different than the previous result. And that's because once a block has been copied to the snapshot area, it's never required to copy it a second time. So larger blocks in this sense are more efficient than smaller blocks. So there's always a trade-off between block size. And this is an example of, in one case, smaller blocks are better, in the other case, larger blocks are better. So now with our improved snapshotting technique, we've lowered the I/O overheads. And when the change block with early release lowers them even further, the I/O overheads are as low as about 20%. And I want to point out an anomaly we found in this study. So this result is with a high bandwidth of 1 gigabit per second. And in this figure, I'm focusing on a single trace out of the 500 that we decided to focus in for this result. And the horizontal axis is the fraction of the transfer period. And the vertical axis, again, is the cumulative fraction of write I/Os that cause snapshot I/O. Now, the red line at the top is with a high throughput bandwidth, 1 gigabit per second. It only took 8 seconds to transfer the dirty data in this example. The bottom line in green is actually with a much slower network bandwidth, T1 bandwidth. And it took over almost 2 hours. And you can see that the higher the bandwidth, the higher the I/O overhead. And that's because it was such a short period, 8 seconds, that basically every incoming write was to a unique block. There were no overwrites. And so every write caused a write amplification. Whereas with the slower bandwidth, there was time for writes to become aggregated to blocks that had already been copied. And so, in fact, there were lower I/O overheads with slower bandwidth. So it's an unintuitive result. Now, again, it was only 8 seconds. And so perhaps you're saying, well, yes, there's 100% overhead for that short period of time. But depending on requirements of customers, that is something to consider. Next, the previous two results were focusing really on primary storage. And next, I'll focus on the protection storage side of that first diagram. So the question is, how much data needs to be transferred to protection storage as compared to what was written by the application to the primary storage? So our rule of thumb is that about 40% of bytes written by the application actually need to be transferred. So the vertical axis is actually a log scale. It's the fraction of data transferred over data written. And you can see that using a large block size of a megabyte, you can actually have to transfer almost 500% as compared to what was written. And that's because we have a large block size. Perhaps the trace only touched a few sectors out of that megabyte, and so this leads to an overhead. We're transferring a megabyte even though the application only wrote kilobytes in this example. But as we extend the replication interval up to 24 hours, you can see that the amount transferred is dropping off. And looking at the larger block size, the smaller block size of 512 bytes, you can see it starts at 100% because once a sector only has to be transferred once. and it drops to about 40% with a day in between replications. So this was with all of the traces. If we next focus on the highly sequential traces, this is the blue lines, and you can see that they're entirely in overlap because the block size doesn't matter because they're so fully dirty. And again, they start out at 100% and drop down to about 40% of what is written leads to what's actually transferred. And again, this is because if a block is overwritten, it's only the final value at the end of the replication interval that needs to be copied and transferred. If we look at the highly random traces, you can see overheads as high as 2,000%, and that's because a single sector of 1 megabyte was modified. So this leads to dramatic overheads and what needs to be transferred across the network. Next, we'll look at the I/O requirements for protection storage, the I/O per second requirements. So the vertical axis, we've normalized the I/O requirements as a fraction of the primary storage I/O requirements. And the issue is that we could come up with some pure numbers of 1,000 or 2,000 I/Os per second or whatever the pure number might be. But the issue is that protection storage needs to continue to scale in the future with primary storage. So instead, we've normalized it as a fractional relationship. And you can see that looking at all the traces, we have the green lines here, and they start off at around 25% of the I/O per second requirements and drop to around 10%. And so our rule of thumb is that protection storage needs to support about 20% of the I/O per second requirements of primary storage and continue to scale that way in the future. If we look at the highly sequential traces, again, they're very tightly grouped, and they're somewhere above 10% and end around 5%. Looking at the highly random traces, the I/O requirements are much higher, and that's because these traces are just jumping from non-consecutive block to non-consecutive block and have much higher I/O per second requirements. So I want to briefly discuss some of the related work, and I'll direct you to the paper for more details. There have been a huge number of papers about trace analysis, and I would say the most closely related is a paper by Patterson in 2002, the Snap Mirror paper, which also looked at incremental changes and transferring to protection storage. In contrast to that paper, we had a much larger set of traces. We considered varying the block size. We looked at I/O and storage overheads on both the primary storage and the protection storage. And I should point out the snapshotting, of course, is a standard storage paradigm and been widely implemented. But as far as we've been able to tell from looking at the literature, it's very rarely been implemented in the context of replication. The idea that a snapshot may only need to exist for a short period of time and protect a set of modified blocks as compared to the whole storage volume, as far as we can tell, has rarely been implemented. There has been some previous work looking at storage overheads that came up with similar rules of thumb of about 8% capacity overheads for snapshotting. And in contrast to our work, there's been work in synchronous mirroring, where basically every I/O is mirrored at a secondary location, which is effective if the change rates are low or the machines are geographically close to each other. And in contrast, we're looking at backups that are periodic, asynchronous, and to remote sites across a wide area network. So in conclusion, we can return to our storage environment, and now we have better information about the overheads on primary storage related to snapshotting, the network bandwidth requirements, the capacity and I/O requirements for protection storage. And so in conclusion, we analyzed a very large number of traces to better understand incremental change characteristics. We present replication snapshots, which are an improvement over standard snapshotting to reduce overheads on primary storage. And we've analyzed the differences between sequential and random access patterns, which can have widely different characteristics. And I'm not going to read through this set of rules of thumb, but I'll just leave them up on the screen as I answer questions.
So in the case where you avoid having to do a snapshot copy for things that have already gone out, so to speak.
Yes.
What's your assumption about what's happening at the other end? So it seems like you're assuming you don't have to restart, for instance, the replication because the other end lost it for some reason. Is that true? Or?
So you're saying that in the fine-grained tracking, we've transferred a block, we've had confirmation that the data protection site has received it, and so we can unmark it. Yeah. And then what was the question?
So your assumption is that the storage is fairly stable once it gets to the other side?
Yes, we're assuming that there's communication between the primary and the protection, and once the protection says it has it, that's the storage of last resort, and we can trust that. I mean, with any transfer of backups to a remote site, you have to have some confirmation and then trust that confirmation,
Right.
certainly.
Okay. So a confirmation is basically block by block.
It could be, I mean, that was the simple model in this paper. Of course, that might be inefficient. You might want to have groups of blocks at larger units to reduce communication overheads, but yes.
Hi, Nguyen Park from Cloud Physics. Thank you for the talk. I have some questions. So the system seems to be fairly sensitive to sequentiality of the data access pattern. Do you have some sense of the distribution of sequentiality you saw as you defined it?
Yeah, so you asked about the distribution of sequentialness. How many systems were very sequential versus very random? Is that the question?
Yes.
Yeah, so I don't have that figure in front of me. In the paper, there's a figure showing the average amount written per random seek. And it's kind of this distribution goes, whoop, that grows slowly and then rapidly. And the issue is that it was hard to come up with exact thresholds where to say this is sequential versus this is a random trace. And so we basically selected the 50 most random and the 50 most sequential. And so it would be hard to say the distribution there. I'd point you to the paper where we show this figure.
Do you remember the number for what the threshold was for the top 50?
It was about if the amount written per random seek was less than 8 kilobytes, we considered that random. And if it was over 100-something kilobytes, that was considered highly sequential. The exact numbers are in the paper, but it was about those numbers. All right, thank you.